Today, we are very happy to have Yuhsin Tsai from University of Notre Dame. He will tell us about the cosmological particle production and pairwise both on the CMB. Yeah, you can start now. Take it away.
Okay, thank you, Da. Thanks for the invitation, and then it's really great to see all of you, even remotely. So hopefully, Da should give me a virtual tour of your new building or floor. So hopefully, I can also come to visit maybe sometime next year. So today the talk is about looking at some kind of exotic signatures on the CMB that I would say is actually can actually generate pretty easily if we have some heavy particle production during the inflation. And part of the story would be about like if we do have this signal, so maybe instead of the usual way of using the power spectrum to understand get the information from the CMB, and maybe there's some position space search can also be useful. So that's the idea. So these are my awesome collaborators that we are working together on the thing, and then hopefully, I mean, we have the draft ready, but we are trying to collect more feedbacks from people, and hopefully we can finish this soon. So one thing is that Shobik Kumar, who is now a postdoc at Berkeley, and then hopefully he can also find time, I mean, get a chance to visit you at Davis. Okay. So I think most of you have, I mean, already know about CMB, and then have at least have seen this nice picture from talks. So the CMB background would be the particle detector that we are going to use to identify some heavy particle that produced at a very early time in the universe during the inflation time. And then as we know that there's a temperature fluctuation of the CMB, and then there's lots of different physics leaves its information on this temperature fluctuation. So just to as a quick reminder for some basic things about CMB, just in case if you're not working on this all the time, and also set up some language that we will use later in the talk. So the usual way that we make sense of the CMB or taking the data and doing analysis is to calculate either the power spectrum, the 2-point function of the temperature fluctuation, or 3-point function, or in principle, you can do this for even higher n-point function do analysis. Okay. So for example, for the temperature perturbation, like you may have seen this spectrum of the temperature perturbation before, given the size of this 2-point function as a function of the different L modes. So basic idea is that if you go to the right side of the plot, you are looking at the smaller hot and cold spot in position space. You go to the left side of the plot, you go to a bigger hot and cold spot in the sky. So one thing to keep in mind is that if the size of the hot and cold spot is small enough, so that would mean the perturbation, the mode of the perturbation enters the horizon before the recombination happens. Then you get this subhorizon physics that changes the temperature fluctuation due to the photon scattering with the charge baryon, this physics that further process the fluctuation. But if you are looking at the larger hot and cold spot, which only enters the horizon after the last scattering, the correction to the temperature fluctuation is much smaller, only due to some mild gravitational effect. Then you see the temperature fluctuation is roughly scale invariant. Okay, for all the different L modes, you roughly get the same result. And in fact, this plot is plotting the linear scale. So actually, for most of the spectrum, you roughly have the temperature fluctuation to the same order of magnitude. that tells us that the fluctuation in the CMB is pretty much scale invariant. Okay. So this makes a perfect sense of trying to analyze the CMB data using these correlation functions, because basically the physics that happens in the early time, it shows up in some location. It will also shows up everywhere in the sky. So the better way to extract the signal is to do some statistics, and this is like calculating the endpoint function fluctuation. But the signal I'm going to talk about, and also the possible search of the signal, is kind of going in a highly scale dependent way. So breaks the scale invariant. Okay. And the motivation that why we want to look at this is that we are trying to use the early cosmology to probe very heavy particles that produce during the inflation. Okay. So in fact, there is already a program that many people were thinking about these days. It's called Cosmological collider physics that discuss about the production of the heavy particle during inflation and what's the endpoint function signatures that the signal can leave on the CMB. So for example, if you have some new particles, they have some coupling to the inflaton that were produced during inflation time. If you can produce these new particles almost on shell, then you can induce a non-trivial, like a 3-point function of the inflaton fluctuation, and that will end up giving you a bispectral signal, which is basically non-Gaussianity. Okay. So this is a basic idea, and there are lots of studies and papers that have been done on this front. One generic thing of such a signal is that unless you are trying to crank up some mechanism to largely enhance the signal, usually the size of the spectrum you will get will have this exponential suppression, which is related to the ratio of the heavy particle mass versus the Hubble scale during inflation. And you can basically think this is a Boltzmann suppression where the temperature is roughly the inflationary scale. Okay, so we will come back to this kind of suppression again later. Okay, so this directly tells us that if
before going on,
please,
I want to ask you simple, maybe it's like a question or comment.
Yeah.
If you look, this is three-pound correlation function of the delta phi. Why there is a 2-particle vertex for delta sigma delta phi, or this is something?
Right. So you can imagine like you get this from a kinetic term, like an original from the phi square and maybe a derivative of the sigma square. But because sigma, if the sigma changing slowly in time, that's basically you get some background value of one of the derivative of the sigma.
Which means it's 3-particle. This is 2-particle. I mean, delta sigma, delta phi. This 2-particle interaction coming from 3-particle interaction. Put one field to background value, right?
That's right. That's right. Yeah, that's right. So you can actually have both of the things from the quartic coupling, like a phi square derivative of the sigma square and things like that.
Okay.
Yeah. Right. So the point is that if you want to go to an even heavier particle, you will get an even larger suppression because it's hard to produce these particles on shell using the energy of the background. But even so, for the high scale inflation, like we can still have the Hubble scale to be the 10 to the 13 GeV. So we can still use this to probe a very heavy particle if we are lucky enough to get the signal. But we want to go even higher. So this will tell us that because of this suppression, if I want to look at the even heavier particles, for sure, I'm going to get an even larger suppression. So the effect I'm going to look at now is not like I'm going to change the fluctuation of the inflaton everywhere in the sky, but it would be more like I produce the particles, like only a few particles in the whole sky. So the signal would look more like localized signals in position space. That's the price I need to pay if I go to a much higher mass. So if that's the case, then what would the signal look like, and how can we look for the signal? Okay. And that's basically the thing we want to look at here today. Of course, I'm going to explain what's the production of the Higgs particle, how do we get the signal, but the signal we will be looking at today would be kind of pairly produced hotspots on the CMB map. And this is a cartoon picture, of course. So we did a slightly more careful numerical simulation of the signal and put on the CMB background. And then the idea is that you will see the signal as a localized hotspot on the sky. Okay. So this motivates us to trying to look for this highly localized signal in position space, not by doing the power spectrum, but by even more directly doing a position space search. So this is more like, as John will know very well, is like the super cold spot on the CMB that the people were trying to identify and trying to find the physics origin. So that would be the searching position space. And that's the kind of the study I'm going to discuss here today. Okay.
Sorry, I want to follow. So
yeah.
Why this position space search does not have this Boltzmann suppression?
It has, so the number density is much smaller.
Okay.
So the separation would be there, and that's why the number of signals we generate will be much smaller than the total number of coding hotspots that we have in the sky.
Why position space better search better than the impounding function? What's the underlying logic?
Because for the endpoint function, you are basically doing a statistic, right, for the average fluctuation of the hot and cold spot.
Okay.
But if you have so few signals, basically in total, their contribution to the overall temperature is so small.
Are you saying for individual events instead of statistical distribution?
That's right.
Doing something.
But later, when I give you a concrete example, I will still show you the change of the power spectrum. Okay. So here is more like it's a motivation. Like since the signal is so localized in space, so maybe we can also use the cut and count, like what we are searching the signal, like doing the jet analysis, for example, and just to look for the position space signal.
Okay, got it. Thank you.
So as you were saying, so in the end, this may mean that even besides the usual way that we still doing our endpoint function analysis and finding corrections to the power spectrum, we may also be able to use some temperature cuts or isolation cuts in trying to identify the signal, or even do a template map, a template mapping to dig out the signal. Okay, so that's the idea. And in some sense, as I say, it will more like a bit more like a collider analysis in some sense. So first of all, I need to say that the original motivation that I decided to look into this is after reading his kind of a crazy paper from Juan Mondosena. He is trying to discuss, like, is there any chance that we can know that the quantum fluctuation of the universe is from the fluctuation in the universe is from quantum fluctuation instead of just a classical thermal fluctuation. So he was trying to design a model that can generate a pairwise spots in the sky, and then trying to do some Bayes inequality of these two spots. But for him, the motivation is just to trying to think about the quantum fluctuation. So he actually didn't specify too much on the phenomenology of the spot and also about how to produce the spot. But that's the place that got me interested in trying to think how can we write down a concrete scenario to do this, and what's the chance of looking at this pairwise spot. Okay, so the structure of the talk is very simple. So roughly for the first 2/3 of the talk, I'm going to just give you the whole story, just step by step, how does a heavy particle production ends up giving you this pairwise hotspot signal. And after that, I'm going to give you one simple example on position space search of the signal. Okay, so but please interrupt me anytime, and then I can modify the way that we do the discussion. Okay. Okay. So so early universe actually, especially during inflation, is actually provide you a chance to produce new particles that have a large mass. So let me discuss this process. So just to give you a concrete example, so let's just assume our heavy particle comes from a scalar field, sigma, okay? And then let's say this sigma field carries an inflaton-dependent mass, okay? So the sigma field is typically much heavier than the Hubble scale, okay? So it is very hard to produce the particle until maybe there's some local minimum of the sigma mass that shows up when the inflaton was rolling to some value. Okay, so that's just assume this is the case. You can have keep oscillating a spectrum or different potential, but that's just a focus on the case when I have a one local minimum, when I get the minimum mass of the sigma field. Okay, so because the sigma field gets a much smaller mass at this time, so the dominant production of the heavy particle will around this time scale. Let me call as eta star, just as the time during inflation. Okay. So you can, so we just write down an example with some sigma square and then 5 VEV dependent mass, basically from the sigma square phi square term, so that the mass gets some minimum value at some inflaton VEV, and then assuming the coupling to the inflaton has this coupling G here. Okay, so this is the setup. Okay, so G square, phi square, sigma square, basically. The similar potential was also used in some earlier literatures from people from Stanford, and they were looking at some endpoint function signals. But the potential here will look slightly different, and then we also, the focus is also a bit different. Okay. Okay. So at this point, we can write down the equation motion of the sigma field, and it will carry some damping term from the Hubble expansion, and also have carries a time-dependent mass term. Okay. So we can redefine the field, it's just algebra, and then you can get the equation of motion like a harmonic oscillator with a time-dependent frequency. Okay, so this is basically how the sigma field evolve. Okay, so now we want to calculate the production of the sigma field. So how are we going to do this? Okay, so for people who are not familiar with this cosmological particle production, so here we cannot do the particle production like what we do in the collider physics. Like we have a well-defined mass of the particle, we quantize the field, and then we calculate Feynman diagrams. Because here, both the sigma and the inflaton are a time-dependent field. So we cannot do the calculation that we did usually in collider search. Okay. So what we need to do is actually doing this, the so-called Bogoliubov transformation type of calculation by comparing the initial and the final state vacuum state and trying to estimate the particle production. But let me explain the main idea of this. Okay. So remember, we have an equation of motion of the sigma as a time-dependent mass term. So that will mean that if in the initial time, and here let me just take the initial time as minus infinity. Okay, this is the easier way to write the initial time in the de Sitter space. So for the initial mass, I can have a ground state, a wave function. Let's say at a later time, because my mass changes. Okay, if this change of the mass is fast enough, my original ground state will end up to be some linear combination of the new ground state and also with bunch of excited state with a new mass term. Okay, so this is a non-adiabatic process. If I don't get to always follow the true vacuum, then this would be what happened. So if now I'm trying to quantify this field by doing the usual thing, putting A in A Dagger and then quantizing the field, what I will get is the later time raising lowering operator will now become some linear combination of the original raising lowering operator defined in the original vacuum. Okay. So this is the so-called Bogoliubov transform. Okay, it's just because my vacuum now changes in time, because the mass term changes, I can have this relation between the early and late time raising lowering operator. So now let's say I now at a later time, I want to calculate what's the number density of the sigma field, which is 0 in the beginning. What I can do if I take a Heisenberg's picture is that I take the original vacuum and then put in the new raising lowering operator. But in this case, both my B and B dagger actually contains both the A and A dagger defined in the initial vacuum. So I no longer have 0 in my final result because I will actually have an A dagger and the A, and that will give me a non-zero average number density at the later time. And this is how I can estimate the number of particles being produced in the new vacuum. Okay. I'm going to skip the detailed calculation, but I actually put some equations in the backup slides. So if you want to see more details, I can tell you like technically, like what do you have to do when you do this calculation. So if you're interested, I can tell you more details. But here, let me just give you the final result that you can have. Okay, and I'm going to explain the physics meaning of this result. Okay. So in the end, once you get this number density of the particles that depends on the coupling to the inflaton and the rolling of the inflaton, you need to multiply this number density to some volume in the universe that relates to the CMB physics. So there's actually the area of the CMB last scattering times some thickness of the last scattering surface. This is actually the region when for the photon can have that last scattering to happen, which is around this region. So number density comes a volume and give you the total number of sigma fields that sigma particle that you can produce. Okay. So
very
yes,
naive
please.
question.
Yeah.
Sorry, very naive question.
Yeah, please.
Why sigma is always generated in pairs?
Oh yeah, that's right. So I forgot to say. So so first of all, you cannot just produce sigma by itself because you can, again, when you do this vacuum AA dagger thing more carefully, you will see that the energy momentum conservation requires you to produce them at least in pairs. But if you want to produce more of them, you need to give even more exponential separations. Okay. So for this discussion, I'm going to basically, this is a very good approximation actually. You will basically just see them show up in pairs, given that we also don't have many of them to be produced in the end.
I got the 3 sigma, 4 sigma, we got surprised. But why can't we have a 5 go to a sigma process? So
yeah, because when you produce this thing, you actually always have some kind of non-zero momentum, like a spatial momentum.
Oh, okay, okay, got it.
Then,
okay, but phi is the okay, I got it. Phi is the condensated field, has no momentum.
That's right.
That's the reason. Okay, got it. Sorry.
Yeah. Okay, so is this okay? Good. Again, please interrupt me if there are questions. Okay, so this second term here is basically the volume, okay, of this shell here. I just rewrite it into 1 over distance instead of distance, but this is just a volume factor. For the number density factor, you see this exponential separation show up as a ratio of the heavy particle mass divided by this coupling times the inflaton kinetic energy, roughly, the derivative of the inflaton. And we actually know this term should be there because all this production relies on the fact that this change of the state from the initial to the final state happens in a non-adiabatic way, meaning that I want this mass change to be the faster the mass change is, the better. Right. So I don't always follow. I don't get the chance to always follow the true minimum because I still have Hubble damping. So if I change the mass slowly enough, then I don't have this effect. Okay. So that's why if the larger this the change of the mass, which to the linear order in time, which is given by this coupling times the derivative of the inflaton field, the better. And then it shows up because when this term is much larger than the mass of the sigma field, which gives you the oscillation frequency, then the exponential separation becomes smaller, then you can generate more particles. But if it's the other way around, then you get a big separation. Okay, so that's why we expect this exponential separation to show up. But now this is still a pretty complicated expression. So let me just plug in some numbers to really get a feeling about what's the number of signals we can get. Okay. So from inflation, we know what's the time derivative of the inflaton field needs to be, okay, because this determines the primordial fluctuation we see in the CMB. So this is about 60 times of the Hubble during inflation. Okay. And then I can plug that number in, and in the end, the result basically just show up as some number times the H star. Okay, so all the H star will cancel in the end. So I plug in that number, and if I just assume a coupling between the sigma field and the inflaton, let me just assume some mass of the particle during the production, and here let me just even assume it's a few hundred times larger than the Hubble during inflation, then this will end up giving me about 1,000 of the heavy particle pairs in the whole sky, in the CMB sky. Okay, so it's not easy to produce quite an amount of pairs of heavy particles, but still the number is much smaller than the number of hotspots that you have in the sky. Okay. Oh, one thing I can give you. So this definitely depends on what's the horizon size when you produce a particle. And for this number, I assume the size of the spot and roughly the separation of the spot is like you divide the sky into 1,000 by 1,000 pieces. Okay, and that size of the pixel is roughly the spot size I use for this example. Okay.
Yes. After one question.
Yes, please.
Right. I thought you will have the Boltzmann suppression, but this exponential suppression is not Boltzmann suppression, right?
No. Sorry. Yes. So sorry. So when I say Boltzmann, I always say it looks like Boltzmann suppression, but yeah. It's not thermal. Yeah, definitely there's nothing thermal here. Yeah.
Right, because there's no temperature.
That's right. So yeah, sometimes people say that, oh, there's Boltzmann suppression and temperature is Hubble, but it's actually the physics is what I was describing here. So it's nothing, there's nothing thermal here, but it just looks like a Boltzmann suppression factor.
Okay.
Yeah. Does that make sense?
Yeah, sure.
Mm-hmm. Okay. So, but you will say that, okay, so if you produce this 1,000 hotspot, we want to make sure this, even before production with this sizable size of the coupling between sigma to the inflaton, I need to make sure that I don't destroy the slow roll motion already, right? When directly in the equation of motion. So that's why we also need to see if I do have this coupling to between sigma field to the inflaton, how much does it change the slow roll? So the idea is that I can look at the equation of motion for the inflaton field, and then just make sure that this new term I generate at tree level in the inflaton coupling is subdominant comparing to the change of the inflaton potential. Okay, so this requirement will set up an upper bound on the coupling n times the number density comparing to the inflaton rolling that we know, we do experiment, we know. And this actually ends up giving a very weak bound, actually. on the number of the particles that you can generate. Okay, so you can actually generate much more without changing the slow roll motion too much, and simply because this number with this size of the hot and cold spot in the sky, and also plus the size of the temperature it corrects, is actually not that significant comparing to the whole energy density of the total sky. So this is just one tree-level correction to the equation of motion of the inflaton. There's also a loop-level process that this is more like a tuning problem. Like you can radiatively correct the inflaton mass and then destroy your slow roll motion. And this is indeed the issue. Okay. So there is a naturalness problem needs to be solved, and which already has been discussed in several literatures when doing this sigma square, phi square type of model. You can even supersymmetrize it or do some magic to solve it. So I'm going to just assume the models in those literatures, they can work. Well, that's the thing that people will work out. So I would just assume those physics will take care of the radiative correction, and then just forget about this tuning issue. Okay.
Is it,
so here, yeah.
You choose this potential like a J phi minus M square is because of this? Because first of all, the upper bound is very weak, is very large, sorry, it's very weak, sorry, very weak. Mm-hmm. And secondly, they have a SUSY completion. Is this underlying reasons you choose this particular form potential?
No, actually, when I choose a potential, I just write the simplest potential that I can write down for the sigma to obtain the inflaton dependent mass.
Okay, you random choose the potential.
That's right. So, but I just say that there are models that was written trying to solve the hierarchy problem for this type of scenarios. So it's true there will be a tuning problem that here. People also try the slight different potential, like only the derivative term of the sigma couples to the inflaton. And that's actually the potential used in this the Flogger et al. Paper. But the analysis is actually quite similar.
Okay. Oh, you mean the result are also quite similar, like the upper bound?
The result is slightly different, because if you do have this oscillating potential, like let's say, sorry, in their case, they are actually doing a sine and cosine function of the sigma field. So it's like the axon-like particle. So in that case, you have some strict symmetry, but you do have several local minimums show up. So basically, the effect of that is several copy of the production at a different time. But because the way they do analysis and also the focus of the signal is very different. So it's not that direct, the result that does not directly imply to our case.
Okay.
But the idea is kind of similar. Yeah.
Okay, just one. Yeah, got a rough idea. This the result are very sensitive to the potential you are choosing, right? Is this
yeah, so it actually doesn't rely on the data a lot. It only depends on when you are around the minimum for the particle production, what's the shape of your potential around the minimum. So you can always, even if you have a sine function, you can always approximate the minimum by a phi square, sigma square term around the minimum. So the answer is actually quite similar. So actually, I see a. That's right.
Yeah, you can go ahead. Yeah.
What's the spatial separation between the members of a pair?
That's right. So I haven't
just have a distribution of that. Or you'll guess that. Okay, so you don't need to.
I will get to the temperature profile, but roughly it's about the horizon size of the particle production.
Okay. Okay.
Yeah.
Thanks.
That's right. Okay. So in fact, all the thing that is important to hear, I mean, just for the last question, is only about the what happened when you are around the minimum. And then there you can always do a linear expansion of the inflaton in time. So ends up you always get something like a sigma square, phi square among the minimum. so the analysis I'm doing here is actually pretty generic. Like when every time you have a local minimum, and that would be what happens.
Okay.
Okay. So that's the point I'm trying to make. Okay. So that's a basic idea. So let me just speed up a little bit. So then the question is, once I produce a heavy particle, what does it do? How does that give the signal to the CMB? So the idea is very simple. It's just if the heavy particle you produce don't decay right away during the inflationary time, this mass term you produce is going to change the gravity perturbation or the curvature perturbation around the inside the horizon. Okay, so later when the horizon leaves, the old horizon leaves because of the inflation, then this perturbation is frozen. So even if the heavy particle decay or do whatever, I mean, just disappear, as long as this perturbation is frozen, at a later time when photon can travel for long enough so they will enter horizon again, this is going to give locally give a different temperature fluctuation around this region comparing to the region that without having the heavy particle. Okay, so the effect is not coming from the decay and the reheating of the heavy particle. It comes from once I have a heavy particle, it kind of delays or slow down the inflation a little bit. So I ends up having a higher gravity perturbation in that area. Okay, so this is where we get the signal on the CMB in the end. Okay. And this perturbation is definitely has a profile in distance away from the location of the hotspot. Because the mass, once the field is being produced, this mass term can still evolve a little bit in time. And then let me just skip some of the details here. It's just that it's actually better to talk about the curvature perturbation instead of the energy fluctuation or the metric fluctuation, because this is some gauge invariant quantity and remain invariant after the inflation up to re-entering the horizon today. So when I use the word curvature perturbation, this is just some combination of the energy fluctuation and the gravity fluctuation. Okay, so this is just a fluctuation that I generate. So when I produce a heavy particle in the beginning, inside the horizon, it's going to generate some curvature perturbation depending on the mass of the particle. And at a later time, the old horizon leaves and the mass term changes in time. It again generates a curvature perturbation, but with a slightly different value because the mass still involved in time. Okay. So after all the inflation process is done, and when we look back into the sky today, what we will see is that away from the central of the hotspot, there will be a profile in curvature when moving away from the profile. Okay. And we can calculate this profile. There's a standard way of doing the calculation. It's just basically your Lagrangian, you have a source term of the mass that can couple to the curvature fluctuation. And then this is textbook calculation. If you are interested in this, I can tell you more about this later. But you can just calculate the average value of the change of the curvature because of the source of this mass term here. Okay. And in the end, in position space, the size of the perturbation, also roughly the size of the temperature fluctuation, have this form, which is basically the second term here is a combination of the term that gives you the normal primordial fluctuation from the inflation. So this is this 10 to minus 5 fluctuation that we see in the sky even without a heavy particle, times this actual correction terms that is proportional to the mass of the heavy particle. Okay. So in the end, when we write this mass term more carefully, also including this temperature profile, the time dependence correction that I mentioned here, the curvature perturbation will show up in as this profile here, okay, which is the standard value 10 to minus 5, the adiabatic perturbation, times this additional correction, which is proportional to the coupling G here between the sigma and the inflaton, and times this logarithmic profile, okay? So when I look at the spot in the sky and when I look at the radius correspond to the horizon size of the particle production, this change of the curvature is 0. But when I move inside for the small radius, I begin to see an increase of the curvature perturbation when I move into the inner region of the hotspot with the profile. And this logarithmic profile is actually very generic. Okay, this is really just come from the inflation dynamics. Okay, because when I do my expansion of the phi around the minimum, just do a linear expansion in time, because during the inflation, this time show up as an exponential factor. Relates to this is the inflation, right? This is where the inflation comes from. It's a scale factor, has this exponential expansion. And then for the conformal time that we are using here, this is the thing that gives you this logarithmic profile, okay? So for people who are not familiar with the conformal time, basically, this is the time and the distance that we measure, assuming the universe is not expanding. And you can measure this distance just by looking at the size of the spot in the sky today and take a ratio of the whole sky today. And then that's the thing that you can calculate, the relative size of the distance. Okay, so in the end, this is a profile that we will see in the sky in radius. So you can easily calculate the profile like that in the X, Y, Z, the three-dimensional space. But in order to really know how does the signal look like in the sky, you need to map that onto the two-dimensional light scattering surface. Okay, so you need to do some translation of the mapping. And moreover, the calculation we have been doing so far is only for the primordial fluctuation before entering the horizon. Once the perturbation enters the horizon, all this subhorizon physics that I discussed in the beginning of the talk, they will further change the temperature profile. So that also needs to be taken into account. Okay. So actually, I haven't told you if the signal would look like a hot and cold spot yet, even though I keep saying a hot spot. Okay. So if you look at the Juan's paper that I mentioned before, Juan actually just said that I don't know if it would be a hot and cold spot, and I don't care. Okay, let's just call it as a hot spot. And he can do that because he is Matosena, but we cannot do that. So we need to do a more careful calculation. There's an interesting physics that we found here. Okay. So first of all, there's a standard way of once you get the curvature perturbation and you can figure out what's the change of the temperature. And in fact, because curvature perturbation is basically dominated by the amount of gravity that you have. So when you have a larger gravity because of the mass you generate there, it's actually more difficult to the photon to climb out the potential, the gravitational potential to reach to us. So you will actually get a negative temperature contribution around the particle mass. Okay. So before the mode enters the horizon, you actually expect to see parity produced cold spot in the sky from this heavy particle production. Okay, this will be a generic feature. But once you take into account the physics of the baryon acoustic oscillation, you know that you have this the charged plasma and photon having compression and expansion oscillating back and forth. When you include all those transfer function corrections, you actually end up finding that for the size of the spot will be interested in correspond to the CMB hot and cold spot. From these signals, you actually, most of the time you get the hot spot signals. So the temperature actually flips because of this subhorizon physics. Okay. So you end up generating a pairwise pairly produced hotspot. And in terms of the Huang is right. I mean, so even though that he didn't refuse to do any calculation, he ends up guessing the right solution. So you can do this standard calculation, projection, and then including the transfer function corrections, and to figure out the profile of the temperature of the hotspot as a function of the angle away from the spot location. And then you can do this very naive, like a numerical simulation, and by putting in the hotspot profile. So this would be how would the signal would look like for the pairly produced signals you see, and then the color just gives the temperature. The yellow is the hotter temperature. And this does depends on when did you produce the heavy particles with the different size of the horizon. Okay, so you do see there's some non-trivial oscillation of the temperature for some profiles. Okay. So this would be the signal that we expect to see. Oh, sorry, and the separation, you can estimate the size of separation is basically of order the horizon size during the production, basically. Okay. Okay, so first of all, any questions about the signal production and the profile?
Maybe another very naive question. Can you go back to the result when you calculate the effect? The previous slide, this one. This formula tells us if there's no adiabatic fluctuation, there's also no this heavy particle alone cannot generate a curvature profile, right?
No, sorry. This expression here is very classical. Okay, so this calculation here is just to say if you have. Oh, sorry, you are right. So that's right. So here. Oh, you are talking about this G value here.
No, I'm talking about the adiabatic fluctuation. The theta sigma is proportional to the value of theta AD adiabatic.
That's right.
I'm trying to understand. I think the result should be correct. I'm just trying to have a very intuitive understanding why is it proportional.
Proportional to the adiabatic.
Yeah.
I think this term, yeah. So it's so this fluctuation. Okay. So basically, a adiabatic fluctuation simply comes from basically the slow roll. Basically, the phi dot over the h square over phi dot is this adiabatic perturbation.
Sure.
So here, what I'm doing here is actually I just pull out the terms that contains the inflaton rolling term, because when I do a linear expansion of the phi, there is a time derivative of the inflaton, and then there is also a Hubble term that shows up because everything is in unit of Hubble.
Okay.
So that combination is the same combination as the adiabatic fluctuation, and then I just leave the rest of the term here. So.
Okay? I think okay in the sense that the Hubble constant determines everything. Determines every.
That's right, and then you still have the phi dot in your mass term, and that's basically just give you the slow roll parameter.
Yeah, Hubble is easy. Okay, sure. Thank you. Got it.
Yeah. Okay, so I think I'm probably doing things too slow than what I want to do. But for the last of the 10 minutes, let me just give you a feeling about how plausible is it to find this pretty localized signal if I'm doing a position space search. And I will give you one result if I also calculate the power spectrum of the signal. Okay. So because of time, I will skip some more details here. So basically, one thing that we can do is that once I know the signal profile, and I roughly know what's the number of signal, I can add the signal image on top of the CMB background. And then just to test how good it is that I can dig out the signal, I can just numerically generate some CMB background by only considering the primordial fluctuation. Okay, there are other backgrounds, of course, but let's just look at the primordial fluctuation. So as you can easily see that it's actually not that easy, even though I keep calling them as a hotspot. It's not that easy to just pick up the spot by eye. Okay, so in this case, so look carefully. Like this image here only has a fake CMB background I generate numerically. And this image here have a signal plus background. I don't know. Hopefully you can see a little bit of difference here. Okay, you see a few hotspot signals in some region. Okay, and which is actually not that easy. But the more important thing is that you actually see a more significant pairwise hotspot already in the CMB, just totally due to the thermal fluctuation. Okay, so in order to tell that if we can really do some position space analysis or not to dig out the signal, we actually need to give a try to try some numerical examples trying to see this. Okay. I don't have time to talk about background, but roughly when we're really doing the search, which we haven't done here, and we are not doing this work, but if we really want to do, we also need to consider the instrumental background and also foregrounds from the localized objects like galaxies and stars and stuff. And this is also the background that the normal CMB search need to get rid of. So there are tools that, for example, I can compare the different temperature map at the different frequency band, and because these compact objects, usually give you a signal with a much higher frequency, so you can compare the different map and trying to subtract this foreground. For this analysis, I'm going to assume the same thing can happen. Because our signal actually have almost identical frequency and the thermal distribution as the CMB, besides a little bit of change of the temperature fluctuation. So what I'm going to do is to say that roughly follow some of the analysis in the Planck. Is not to follow the Planck analysis, but I'm saying that I'm going to only assume that only 60% of the image in the end can be useful. Okay. Depending on the frequency of the map, or also depending on the type of analysis, the Planck usually use around 40 to 60% of the sky to do the analysis. And here, let me just assume in the end, after the detector noise, the bad pixel, and also the subtracting foreground, I have roughly 60% the image that I can use. Okay. But besides that, I'm just going to assume the only background I'm going to have is from the background thermal fluctuation. Okay. So in this case, I'm going to try to dig out the signal. Okay. So you will say that, oh, I mean, if the signal is very hot, then it should be easy. Just put a temperature cut, and then you should be able to see the signal very easily. Okay, why is it difficult? But as I already showed you before, the temperature fluctuation of the CMB is actually pretty big. Okay, so the size of the signal I show you is roughly the coupling divided by 2 and times some primordial fluctuation, which is about 27 microkelvin. So even if my coupling is order 5 or something, I will only get something closer to 100 microkelvin. But if you look at the temperature fluctuation of the CMB, which is also about 100 microkelvin, so the signal we call as a hotspot is actually only within 1 or 2 sigma for the temperature fluctuation in the background. Okay. So even though I say the primordial fluctuation that people usually talk about is 10 to minus 5 times the temperature of the CMB, which is 27 microkelvin, the actual temperature fluctuation is much larger than that. And because when we look at things in position space, when we see a pixel, a hotspot, it's actually the sum of the temperature for all the different mode or L mode together. Add them together and give you the position space fluctuation. Okay, so that's why in the end the temperature fluctuation is much larger. And this is basically you can write down the correction. So one thing you can say is, oh, maybe we don't want to sum all the temperature fluctuation from the lower L mode to the higher L mode. So one thing we can do is to cut the sky into smaller squares and take the average temperature of each little squares and just subtract my map using that average temperature in each smaller patch. And that will get rid of the temperature fluctuation from the larger size structure. Okay, so if you do that, you can actually reduce the temperature fluctuation quite a bit. So that can help the search. Okay, so that's one thing that you can do. Another thing that you can do is that you can say, oh, for the random Gaussian fluctuation of the temperature, it should be difficult to have some two fluctuations that above the temperature cut in the nearby location. So I should be able to use some group things into cones and then just require more than two very hot spots, and I should be able to suppress the signal. And in principle, that's yes, but turns out, again, when we do the search in position space, the background signal also likes to show up in pairs or in the several hotspot pixels. Because again, when I've set a very hot spot, the only chance that background fluctuation can pass that high energy temperature cut is to have the temperature with a different size stacked on top of each other. So you have a big continent with a slightly larger temperature and plus some bigger islands, smaller island, and put a mountain so that you can pass the high temperature cut, which is like the sea level here. So the location that you see a very hot temperature cut, you actually get a very good chance to also see another high temperature spots and a nearby location. So that's why this group things into a cone actually helps, but not help as much as we want, okay? But still, this is what we get so far, because in principle, that's actually the thing we're exploring now. In principle, we can use a better template fit to identify the signal or using the machine learning process. Actually, that can also identify the signal pretty nicely. But that's just trying, let me keep things simple. So do this stupid temperature cut, and then also just draw things in the cone and identify the signal from the background. So when I put a high temperature cut, I only have some surviving pixels that shows up. And then I can draw the cones and make sure I have more than one pixels that show up and then identify as a signal. Okay, so that's the simple thing I'm doing here. So let's just see how good does this work. Okay, so I only use 2 or 3 more minutes. I hope it's okay. So one thing that we do.
It's fine, it's fine.
Okay, so is that, so we generate about 5,000 maps with and without the signal, okay? And then for each of them, we do exactly the same search, okay? And then trying to see in the end, we do see a significantly larger number of events being detected in the signal plus background scenario, okay? Because there can still be a lot of fake signals being identified. So we need to take that into account, okay? So for example, like these 2 images, you see that the signal, when we have also the signal involved, we get 1 more cones being identified, which comes from the signal image. But at the same time, we will lose a lot of signals also from showing up in the cold spot in the CMB background, then we lose the signal. Okay. And then we can calculate how many signals we need in the end before putting a cut, so that we can see a 2 sigma axis comparing to the thermal fluctuation background. Okay. So just to give you one example, that if we are looking at the signal with the horizon size to be about 100 megaparsecond, this is about the size when we cut the sky into 100 by 100 pieces. Okay, so this will be the size of the pairwise spots. Okay, if this is the horizon size we consider, and if we consider the coupling to be G equals 3 between the sigma and the inflaton, then in the end, a 2 sigma axis will require the whole sky to have about 600 and about 700 signals in the sky. Okay, within all the 10,000 regions roughly that we can have in the whole sky. So I can go back using the same equation that I showed you before to figure out what's the ratio of the sigma mass versus Hubble. And this would be about 200 of the mass divided by the H star. So if we get to see the signal like this, even though it's only 2 sigma, of course, so it's not a discovery, but this already corresponds to a pretty large ratio of the mass divided by the Hubble, okay, to be a few hundred. Okay, so this is a very heavy particles being produced during inflation. Okay, and the trick we use here is actually easy to understand. The reason why we can get such a larger signal is that we get the production from this non-adiabatic thing. So basically coming from the kinetic energy of the inflaton, like it really depends on the inflaton rolling. So in the end, this mass here is about twice of the G times the phi dot. Okay, so that shows up in your exponential separation here. So if you plug in this number, you get the exponential separation, to be about 10 to minus 5 here. But that will, in the end, plus some other enhancement of the volume and everything, will give you this number of signal. So this is the size of the mass that we can probe by doing this very naive and very simple count-and-count search. It's a stupid count-and-count search. I mean, we can definitely do much better than this using a more detailed profile of the spot.
Yes. For bigger M naught, don't you have a stronger exponential suppression, then you get the smaller N sigma?
That's right. So then that. Oh, sorry. Sorry, I keep saying it wrong. So sorry, you're right. It's
okay.
It's a lower bound. It's like saying that N needs to be larger than this. If I'm setting the exclusion bound, if I want to see it, I want the mass to be smaller than this value. Sorry, maybe I said it wrong in words. Yeah. So this is the lower bound is the exclusion bound. If I don't see, I want to hide the signal. The mass needs to be larger than this. Yeah. Okay. So coming back to the power spectrum, we'll say, okay, so now I populate this number of signals, 700 signals in the sky. And with the temperature profile I know, I can come back and do a numerical simulation, come back, calculate what's the correction to the CMB power spectrum. Okay. So here I show you the correction to the CMB power spectrum. And this green curve here is the difference between the temperature spectrum with and without the signal. Okay, and the gray band here is a 1 sigma fluctuation given by Planck for the current search. And for this region we are looking at, this won't be able to further improve too much because this is from the cosmic variance, like the finite size effect of the universe. So this is basically the uncertainty we will have. Okay. So the fluctuation we see in this one specific example is a little bit larger than 1 sigma for several L bins. If you calculate the total size of the chi-square, and also if you only zoom into this region of the space where you have a larger uncertainty, a larger deviation, you roughly get something slightly below 2 sigma. Okay, actually much below. It's like 1.6 sigma level. Okay, if you are doing this. But in fact, when we do the CMB search and trying to do a fit using lambda CDN, this is actually not what we do, okay? What we do is we take the whole spectrum and change the 6 parameters in the lambda CDN and trying to see if the lambda CDN fit agree with the data with certain number of sigmas, okay? So the usual way that we do the fit, we actually use all the bins to do analysis. And actually the significance would be diluted by a lot when I also allow the other lambda CDN parameters to vary, okay? So just to give you an idea that if I, in the end, need to change the whole thing to the 1 sigma level, I will need the total delta chi-square to be about 70, okay? So in this case, this amount of the chi-square is actually pretty insignificant, okay? But this is not a precise study. If to do a precise study, we also need to do the scan, to do a numerical scan of the lambda CDN parameter. But even if we really zoom in and trying to identify the signal, this will still be smaller than 2 sigma level. So this is just to tell you that at least in this one example, the position space will do a better job than the power spectrum analysis, okay? Okay, so this is all the thing I want to say. So just to conclude, so if you have a mass that have a inflaton dependent, a particle that carries an inflaton dependent mass that have some local minimum, then you have a chance to produce a particle around that minimum. And once you produce the particle, if the mass is large enough, you can generate position space signals show up in pairs. And then in that case, you can either use the position space search or the power spectrum analysis to find out the signal. There are many interesting things to think about. First of all is to improve the analysis. As I said, we're trying to use some like a wavelet technique and some machine learning process. It's just to provide a better template, trying to dig out the signal. And that's one thing. And the other thing is that besides the CMB spectrum, this thing is also going to change the distribution of the galaxy or the lensing, the shear lensing measurement. And there can be other signals that other than the CMB signature. So let me stop at here. Yeah, thank you.
Thank you. So maybe we can collapse.
Thank you.
Any questions? John? Yeah.
Well, all other people disappeared.
Yeah.
Yeah, so
Went a little overtime.
that's right. Yeah, sorry about that. Yeah. This also happens in our Notre Dame. Oh, I shouldn't say that. You are still recording. Yeah. But anyway, this also happens in our seminar too. Yes.
Since there's only us, maybe we can go to a discussion session.
Yeah. So.
We can stop recording when you.
That's right.